Here we go. We're recording. Slideshow from current slide. Let me go over these couple of other announcements. Sorry. Before we get going too far on this. As I started to say, this is rather a strange week in several senses. Today's kind of normal, if there is such a thing. Tomorrow, however, I do have a doctor's appointment at 8 o'clock in the morning. My labs are at 7 o'clock in the morning, and hopefully I'll be through with that by 8:30 or 9ish or so, but we've already made up the class, differential equation class, so it will not be meeting tomorrow. So I may have office hours then, whenever I get back from the doctor's office until 11. So that's a little unusual. I don't usually have extra ones, but this time I do because we already had that class last week. But I definitely miss my Tony, right? I can't read my book here with this light glaring in my eye. Okay. I was just saying, this week is rather a strange week, and I'll try to fill it. Today's fairly normal. Tomorrow, though, I have a doctor's appointment first thing in the morning. In fact, I don't even come to campus. I go straight to the clinic and get blood work done. Then I have a doctor's appointment. Hopefully, I'll be here maybe even as early as 9:30. Probably not that early, but sometime in that time frame. I do have a 11 o'clock class that will meet as normal. And then, because I missed my 8 o'clock class, we're making that class up at 12:30. So that means my office hours, which normally on Tuesdays are 12:15 to 3:15, they will be 1:45 until 3:15, with lunch somewhere in there. Okay. So that's tomorrow. Wednesday, I think, as we were just talking about, I think it's more of a, oh no, it's not quite a normal day because of this. It has nothing to do with office hours, but it has to do with this. Are any of you in an 8 o'clock class Wednesday morning on this campus?
My wife is.
Yeah, I told her about it this morning, okay? I think she was in here when I told her. Fire drill. This Wednesday morning, 8:30. So if you're on campus in this building, be prepared to participate in the fire drill. Now, if that's going to be, now you'll probably be down tutoring, is that right?
I'll be here.
Oh, 10, okay. All right. So, yeah, you'll be out. But if any of you are in the library or something like that, know where your closest exit is and go for it, okay? Now, it's not going to be treated like a fire. There's not going to actually be the alarm pulled. They're not going to do that. But they will, the campus police will come around and tell us it's a drill, okay? Now, the thing I read yesterday, which I guess they sent out Friday, but I didn't see it until yesterday, to me was wrong, and hopefully they're going to get it corrected. They were saying is that for everybody to go out the back side of the building, okay, and all go through those doors that way. I said, this is not how we should be practicing, because that's not what we would do in the case of a fire. You go out the closest exit, not everybody go out one. That actually would be more dangerous than doing it the right way. So I'm hoping we'll go out the way we're supposed to go out. Here we are, right up here. We would go out this exit here. Now normally we go down to this parking lot here, the one that you see right out there. But I think they want everybody out basically under the sign there, on the interstate. So we'll go out the right door, but then go around the side of the building, which you wouldn't do during a fire either, because you'd be walking right next to a burning building, which you don't want to do. You want to get as far away from the building as possible. But since we know it's just a drill and the building hopefully will not be on fire, we will go and go to that parking lot. So that's I think they want to talk with everybody then when when they're there. That's the only thing I can figure why they were saying that. But I sent an email and said, look, we ought to do it the way we're supposed to, the way the instructions say, go to the closest exit, go out. Then if you want to meet somewhere else, we can do that. But we shouldn't go.
Be sure to stay so many feet away from the building.
Yeah,
the
yeah,
whole
exactly.
time, right?
Well, you should, but you can't get between the two buildings doing that, So, but we can get out the building and then go to one location, which just explain to everybody. So hopefully that's how it will be done. So that's that's Wednesday's strange thing. Thursday, we got a faculty meeting. So if you have a class that meets 2:30 in the afternoon, if it's a full-time instructor, the odds are there may be some adjustment to the class. I've got a class at 3:15. We're going to meet at 3:15. It's a mini-term class. We can't afford not to. I got permission from it. It's done. But check with your instructor in case you have a meeting after 2:30, say between 2:30 and 4:30. Check with your instructor and make sure. But there is a faculty meeting. But my office hours then normally are, here, on Thursdays, 12:15 to 3:15. On Thursday, it'll be 12:15 to 2:15 because the meeting starts at 2:30. And Friday is sort of a bad news, good news situation. You've heard those, right? The bad news is Friday's a holiday. There's no school. Campus is closed. The good news, though, it doesn't affect us any. We don't lose any class time. All right, good deal. All right. So that's Friday. Okay. And then I think next week is a bit more normal. I hope so anyway. Enough aberrations for a while. All right. Any questions on anything we've covered up till now? Okay.
And also, tomorrow we vote.
What's that?
Vote.
Oh, yeah. Please vote. Everybody, do not fail to vote. Okay. Man, please vote. I did read some interesting things, and this is not to influence voting or anything, but these are just dumb things. Since, I don't remember when, but for quite a while, did y'all read this in the paper? On the election years, when LSU has played Alabama, when LSU has won, the Republican has won, and when Alabama's won, the Democrats won. For what that's worth.
That's odd.
That is really odd. And I also heard that when the World Series went to 7 games on an election year, if the American League team won, the Republicans won. If the National League team won, the Democrats won. Yeah, it's got to be, yeah. But that one goes back many years. And then there's another one. The Washington Redskins, if they win the last game, the game immediately prior to the election, if they win it, one party wins, and if they lose it, the other party wins. And that's gone back for many, many years. They did play their last game. I didn't know they did this, but it ended in a tie. So who knows what's going to happen? But anyway, those are just, I read those in it was a dumb piece in the paper, What's that? Yeah, right. John Archibald. I don't know if y'all know. He's a columnist. He had looked up these things. What's that?
Cartoons. Never mind, that's not. He writes for AL.com.
Yeah, right. Yeah. He's a pretty good writer too, it seems like. Okay. Any other questions or comments or other things? But like Cameron said, please vote. Don't forfeit your right. Okay, and it is a right. As some other signs around campus have been saying, politicians didn't give you the right to vote. The veterans did. Okay, never mind. Okay. Another issue. All right. We are in the middle of page 724, chapter 13, section 13.5. we have been talking about motion in 3 space, of course, and specifically about our velocity vectors, acceleration vectors, and before that, our tangent vectors, which are related to the velocity vectors, and in some senses, our normal vectors, which in a little sense are related to the acceleration vectors, but they're also related to velocity vectors. And we're going to look at a special case first, and then we're going to look at the more general case. Special case is that of uniform circular motion. Now, what do we mean by uniform motion, period? Constant something, and generally constant speed, okay? So when we say uniform circular motion, we mean circular motion following the path of a circle at a constant speed, where v, the vector v, has a constant length, also called magnitude, that's also called speed, okay? But it's constantly turning, continuously turning, because you're going in circular motion. And velocity is a vector, and that vector has to be changing directions, but not changing magnitude, okay? The acceleration vector, in this case, is centripetal. Most of you have had physics, right? If you haven't, there's a new word for you, or maybe one you've seen before. But that means center seeking, centripetal. Always points toward the center of the circle. You've got to be accelerating this way to change the velocity to bring it around that way. And when you have uniform circular motion, that is always toward the center. Okay? Centripetal acceleration. All right. Now, I think example 5 is next, and that's coming up. I think we'll just write on this slide. It may actually be helpful for it. Okay. Sorry. Really talk. Says find A of t. Let me get my pen back to black. A of t, vector A, acceleration vector. I can't get the arrow to draw. And the magnitude of the acceleration vector as a function of time. Okay? For motion around a circle of radius r, okay, so let's just use their drawing here, make that radius constant r with a constant speed v. So the magnitude of this velocity vector is v, okay, constant speed v. Find A of t and the magnitude of A of t. All right. Now, there's a couple ways you could approach this. I think the most reasonable, and I hope sort of by now you'll find it logical way to do it, is parameterize that circle. How would you parameterize a circle of constant radius, capital R? Circles all have. And we can, for convenience, center it at the origin. Nice. So what would be that circle then? R of t. Well, what if I said I would like you to parameterize a unit circle centered at the origin? What would that be? Second? Cosine c t sine t. Very good. And here's Victor. Okay. Sorry.
That would be multiplied by r, wouldn't it?
That's it exactly. That's why cosine t sine t would be a vector who's a unit vector, a unit circle, and if you put r in front, or put r cosine t, r sine t, either way, r is a constant, that would be your vector of of radius r. Okay? How does that help you get a of t? Oh, yeah. So let's first take a first derivative. R prime of t, which by the way goes by what name? V of t. Okay, and what would that be? That would be what? R times negative sine t cosine t. There we have it. Okay? Now let's take that second derivative, r prime of t, r double prime of t, which should now be our acceleration vector, which is what the first part of the problem asked for, and what would that be? R negative cosine t, negative sine t. All right, that's it. That should be our r double prime. Okay? And oh, wait a minute. Okay. I left off something. To generalize it, we need an omega in there, which omega is our angular frequency. Angular. Yeah, that would be the best word for angular frequency. They haven't really, I don't recall that they really focused on that anywhere before, but that is, to be most general about it, you really need that in there. R omega, R times cosine omega t, sine omega t. That gives you the frequency at which you're going around. So then, when you take the first derivative, that brings an omega outside, but you still have these on the inside too, because chain rule. Okay? Each of those has that. And then when you do it a second time, that gives you omega squared. And of course you have the omega t and omega t there. So sorry about that. R omega squared minus cosine t sine squared. So that's our acceleration vector. First derivative of your velocity vector, second derivative of your displacement vector. Okay. Now, what's that? Yes, exactly. And why they did a v of t, there is a reason for that. Let's go and do what the velocity is. They told us it had a constant velocity v. I wrote it down here, but let's actually find out what that is. The velocity vector is the magnitude of, the speed is the magnitude of that velocity vector. This is our v, v of t. What would that be? As it is right there? Or you mean put it back in?
Or could we keep that out?
Keep it out. Because, yeah.
So R omega.
It's going to be R omega. You're absolutely right. Square root of?
Negative sine omega t squared.
Which is?
1.
1! All right, good. Yes. That's going to be 1 because this part has a magnitude of 1. That's still a unit vector. Okay? Right, okay. So there's this. And this is the reason we did that. To get that v, the speed, constant speed, was r omega. Because omega is a constant, r is a constant. Your speed is a constant. Okay? So you really don't need the t dependence there at all. It's a constant speed. Okay? Now, let's do our magnitude of your acceleration vector. That's the second part. What would that be? It looks incredibly easy. It is. R omega squared. Okay? And if you wanted to rewrite that some way, you could write that as V omega, because V was R omega. Or if you wanted to write omega is equal to V over R, you could have written this then as R times V squared over R squared, which would be V squared over R. And I believe that when you took physics, or even physical science, or whatever, you probably found that your centripetal acceleration had a magnitude of V squared over R. This is what they typically teach.
Would that be that under the speed? Would that be a capital R?
Oh, yeah, I'm sorry. It's a capital R. Yeah, no, yeah. We don't have any little r's in here. Yeah, capital R. V squared over R. Perfect. Very good. Okay, so several things you can do with that. The vector A of t is called the centripetal acceleration, has a length of V squared over R, it points toward the origin, or center of the circle, wherever that is, center of the path, because A of t is a negative multiple of the position vector. So if you think about this, your position vector at any point, it's always pointing this way, and your acceleration vector would then always be pointing in exactly the opposite direction. I drew it there so I would draw on top of it, but for this one, at that position, there's your displacement vector. Your acceleration vector is pointed exactly opposite it. That's because this is exactly opposite the direction of this, with a different magnitude, of course. This has magnitude R, this has magnitude R omega squared. If omega is a small number, then this is shrunk some. If it's a big number, it's actually expanded some. It's always toward the center of the circle. And of course, your scales will be different too. All right. Now, here, I need somewhere. The constant omega, lowercase Greek omega, is called the angular speed because the particle's angle along the circle changes at a rate of omega radians per unit time. So that's called your angular speed. I was calling it frequency, which is quite the same thing, but it's related. Okay. Now, that's for the special case of uniform circular motion. That acceleration vector is always pointed toward the center of the circle. Always centripetal in nature. Center seeking. Now, in general, though, that's not the case. Okay? Velocity could change in two ways. Here, your velocity was changing only in its direction because its magnitude was constant. So that was change of direction only. But you see, your velocity can change for another reason. It can change because it's speeding up in the same direction, or changing direction at the same speed, or changing speed and changing direction. That's the general case. So when you have that, you always have, if it's going in any kind of curvilinear path that is curving at all, then it's going to have a component in the centripetal direction, but also a component in the tangential direction. That's what we're talking about. Centripetal would then be the normal direction. So we have noticed that V of t can change in two ways, magnitude and or direction. To understand how the acceleration vector encodes both types of change, we decompose A into a sum of tangential and normal components. Okay? Recalling that, I think I'll go on to the next slide because we're going to use this anyway. Recall the definition of the unit tangent vector. Can anyone tell me what the definition of the unit tangent vector is? The velocity vector, which is always tangential to the path, divided by its magnitude, v of t, because that makes it a unit vector. The velocity vector is always tangential to the path. To make it a unit tangent vector, divide by the magnitude of v of t. Got it. Okay? Now, can you tell me what the unit normal vector, how we defined it? Okay. I was starting to do it in Leibniz notation, but the book doesn't, so I won't do it either. That's t prime of t. Okay. Now, here I get myself into a little bit of a problem. The unit tangent vector is a unit vector. The first derivative of the unit tangent vector is not necessarily, and in general not, a unit vector. Even though the tangent vector was, its derivative is not. So I'm going back to place just a regular vector symbol over that, not the unit, because I don't want you to get confused, over the magnitude of that same derivative of the tangential vector. Okay, it's the derivative of the unit tangent vector, but it itself is not a unit vector because it's now a derivative. Okay. Now, let's go back to v of t. How could we describe that v of t? For instance, solve this equation right here for v of t. And what would that be? Wouldn't that be magnitude of v of t times t of t? Would you agree with that? Okay. And of course that is, okay? Because the velocity vector is always tangential to the curve. The magnitude of that is this, and the unit vector in that direction is this, because that's what the unit tangent vector is. It's tangential to the curve in the same direction of the velocity vector, but it's just that. Well, we also know that the a of t is v prime of t, don't we? Okay, well, let's take the derivative of that. Well, the derivative of that is, that's a product rule, right? So what would that give you? You can do it either way you want to. What would you get? How to do a product rule? Say that again. Oh, okay. D over dt. I couldn't understand what you're saying. Yeah, of what? V, is that what you're saying, or t? V, okay. Magnitude of v of t, okay, times t of t, plus magnitude of v of t times dt dt. Is that what you're saying? Yeah, agreed. Okay. Now, what is the first derivative of your velocity, of your speed? Okay? Your speed, that's what this is. Magnitude of your velocity vector, that's your speed. Okay? The first derivative of that would be how the speed is changing. Well, speed is always tangential to the curve, right? So how that's changing would be, basically, you can think of it as the acceleration tangential to the curve, right? So we can name that goodness gracious, AT. That's the scalar component of the acceleration vector times the unit tangent vector, because that's in the direction of the motion, okay, plus, well, what is your dt of t? Isn't that precisely that? Okay. Well, that is, to solve for this, t, I'm going to write it this way, dt, that's what this is equal to magnitude of the unit tangent, not unit tangent, but the tangent vector times the normal vector, right? Just sort of like we did before. That's what this is. So this is the speed, magnitude of v of t, times your magnitude of t prime of t times your unit normal vector. Now, this product here then is the component of the acceleration that's normal. In other words, sort of that centripetal component, okay? So this would be your A sub n, okay? Well, what is that A sub n? Well, here's what it is. But let me see if I can recall exactly what that is. Now, what's that? Exactly, okay. I wondered if you had picked up on that. I was going to refer you back to, and it goes quite a ways back, so I was hesitating doing it because you've got to go so far back to find it. Yeah, there we have it. T prime of t is, well, that's not quite what I was looking for, but it is portion of it. There it is. Equation 2 back on page 713, this t prime of t, right there, magnitude of that is k of t times v of t. So this is your curvature, scalar quantity, times your velocity. Speed, okay? Well, but this is your speed. The magnitude of your velocity is speed. So this is now your let me abbreviate it this, v prime of t, because that's the derivative of your magnitude, your speed. That's v time of t in the direction of unit tangent vector, plus your curvature as a function of time, times your speed squared as a function of time in the direction of your unit normal vector. Okay? And that then gives us exactly what we have here. Your acceleration vector has a tangential component, which is just the first derivative of your speed. That's what this is, okay, in the tangential direction. And your normal component is your curvature times your speed squared. Okay, that's derivative of speed. This is the actual speed itself, and that's the normal component. So here, this pretty much sums up everything we were saying. This is how you break down the acceleration into a tangential component, which is the derivative of your speed, tangential direction, plus a normal component. This is a component of the vector here in the direction of the normal vector, and that component is the product of your curvature times the speed squared, okay? Which gives you your, what I like to think of the centripetal component, that center seeking, okay, which is your normal component. Okay, let me see where we are. Oh, I turned too far back. Let me get back to where we were. Okay, so that's the top of page 725. Now they do an illustration here, which I think is a pretty good one. Here we have motion along this green pathway. Blow it up some. Why did it go there? Okay, that's better. Okay. Here's motion along this green curve here. Certainly not circular motion, but it is curvilinear motion, which means it's going to have a component in the normal direction and a component in the tangential direction. Okay? Okay. Now, wherever your center is, I assume it's probably down this way, there is your displacement vector. Your velocity vector is along the direction of the unit tangent vector. In fact, that's how we define the unit tangent vector. But the acceleration has a component along this way because you see, if indeed it's moving like this, it has to be speeding up in that direction. It's not going in a circle. A circle would be coming around here, so it must have enough speed in this direction to yank it out further that way. So it has an acceleration in the direction of motion. Okay? That's your A sub t. Okay? But it also has, because of the curvature, it has a component toward the center. And that's your A sub n here. Okay? And when you multiply your component in this direction, add that to the multiplying your component in this direction, that then gives you your acceleration in this direction. Now, cat doesn't look like this to me. That looks longer. I don't know. That to me just looks longer than that. I don't know if it is. Maybe it's exactly the same. But because you have a big shape around this one, a little around that one, it makes it look different. Anyway, that's how you work this out. Decomposition of your acceleration vector into a tangential and normal components. Okay. Now understand the normal and tangential components are always changing. Okay. Right here they're there. Up here they'd be like this. You know, they would be a different frame of reference from this one. So that whole process is changing constantly. Okay. Now, I think that's where the centripetal, the conceptual insight comes into play. The normal component, A sub n, is often called the centripetal acceleration. That's what I've been calling it, especially in the case of circular motion where it's directed toward the center of the circle. Okay. Well, this doesn't actually have a circle because it's not a circle, but you know, it's still pointing toward the shape's center, you might say. The tangential component, A sub t, which is the first derivative of the speed, is the rate at which the speed, v of t, changes, whereas the normal component, kappa times v squared, describes a change in v due to a change of direction. These interpretations become clear once we consider the following extreme case. A particle travels in a straight line. Everything's tangential. There is no normal component there, okay? The direction does not change, so the kappa is 0, and the A of t is just strictly v prime of t in the direction of the unit tangent vector, parallel to the direction of motion. Particle travels at constant speed and along a curved path, then v prime of t is 0 because the constant speed, its first derivative of the speed would be 0, then the acceleration is strictly in the normal component. All right, so the next problem is this one. Giant Ferris wheel in Vienna. I Didn't know. I guess that may be one of the largest, if not the largest in the world. It says erected in 1897, celebrate the 50th anniversary of the coronation of Emperor Franz Joseph I. That's the Holy Roman Emperor, by the way, if you didn't wonder what was he the emperor of. They also considered it the Austrian-Hungarian Empire, so that's the other way you could think of that. But anyway, giant Ferris wheel in Vienna has a radius of 30 meters. Okay, so this right here, the radius of this, if I could get my screen to stay still, this is R is equal to 30 meters. It's pretty far, more than a third of a football field from center to house. So this is 2/3 of a football field across. That's a pretty big Ferris wheel. Okay. Assuming at time t equals 0, the wheel rotates counterclockwise with a speed of 40 meters per minute. Well, what's that a measure of? I can't write. 40 meters per minute. That is your your linear velocity. That is actually the tangential speed here. I drew it with a curve, but it's actually, so this is your v of t is equal to 40 meters per minute. Change of direction, okay. Change of distance and change of time, okay. And is slowing at a rate of 15 meters per minute squared. So what is that telling you? Okay, your
The negative acceleration.
right. Your a sub t, remember that's the tangential component of your acceleration, is equal to negative, what did we say? 15 meter per minute squared. Okay? Now that the speed is slowing. And this, by the way, is dv dt. Now that is not velocity, this is speed, magnitude of that. Okay. Which is your a sub t. Little, yeah, okay, like you see above. V prime of t, what they call V prime of t. All right. Find the acceleration vector A. This is what we're looking for here. Okay. For a person seated in the car at the lowest point of the wheel. So you can't quite see it here, but let's just assume right down here. Let's see, do you want a different color so we can see that? Pick a color, any color. Blue. Light blue? Dark blue. Okay, dark blue. Picky, picky. Okay. The reason I was going to go with light, I thought it might be more distinguishable. Yeah, but there you can see it. Not well, but you can see it. You see? Blue dot, that's it. The guy's the blue dot. Another blue dot in a really red state. No, I didn't say that. Okay. Yeah, okay. I've got to find where we are. At the bottom of the wheel, can you tell me what the unit tangent vector is? Down here,
So it's moving which way, counterclockwise?
counterclockwise.
So that way. So the positive in that direction.
Very bottom of the wheel. So the unit tangent vector is has no vertical component. It's a unit vector, so that must be 1, 0. Make sense? Unit tangent vector. Because it has to be a unit vector, and it has no component up or down, because it's right at the bottom. At that instant, a little bit later, it's going to have a component. Or that instant, right, you're right there. Okay.
Is that a 1 or negative 1?
Looks like a 1 to me. If you use one to, positive to the right, negative to the left, and they'll sit down 5, 5, 5. Okay. 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 They just chose to say that, but you didn't have to. But it's true. What's the unit normal vector there? What color you want it? I should make it a different color. They've been doing the tangent in red. So let me go back and do the tangent in red. And the unit normal vector they've been doing in blue. And I'm sure they like dark blue too. Okay, and what would it be? Opposite would be back. Say again?
0, 1.
Yes, exactly. Okay, in that sense, opposite 0, 1, because it's pointing upward. So there's your unit normal vector. Red is the unit tangent vector. Okay, got it. Okay. We are told that the acceleration, the tangential component of the acceleration, that's what we did here. The tangential component of the acceleration is minus 15 meters per minute squared. Yes, at time t equals 0. Okay, good deal. Here is Jonathan. Okay, we're only missing Ashley and Javon. Is that right? 1, 2, 3, 4, 5, 6, 7. Yes. Just missing 2. All right. All right. So we know here that the tangential component of the acceleration is that. Okay? All right. So, frankly, we can write the first part right now. This is equal to minus 15. I like to put the units in. I think they leave them out. Meters per minute squared. That's an acceleration, tangential acceleration, and that's in the AT direction. Okay? Now what we've got to do is find the normal component. Okay? Is there any way to do that? Hint, uniform circular motion. This is a Ferris wheel, not a Ferris ellipse or hyperbole or anything else. It's a wheel, it's a circle. So what will be your,
It's always pointing towards the center.
okay, in the direction of the unit normal vector. So since it is, we'll do this in blue maybe. And what would be the magnitude of that?
1.
Not necessarily. What was our centripetal acceleration? We used to say in physics. Just did it a slide or two ago. V squared over R. Remember that? Now what's your V squared? Or the V, we just got it. That's 40. All right, I say 40 and write 400. I don't know what's wrong with the brain. It's just not working well. 40 meter per minute squared over our radius, which was 30 meters. So this is 1600 divided by 30, and this meter will go into one of those two, so that would be a meter left per minute squared. And zeros can go out, and this would be 3 will go into 16.5. Second? 53.3, is that what you said? All right, so that will be, and that will be in the plus direction, plus 53.3. That's approximately a sub n, the component of the acceleration in the normal direction. And that is what they got. Both of those have units meters per minute squared, so we could write this as they do. A is approximately the vector minus 15 without units. Well, no, they're going to put them in a minute. 53.3, and that'll be meters per minute squared. Okay. Yep. All right. Now, here is a pictorial representation of what we were just talking about in a sense, where the radius here is our 30 meters. Okay, we had the movement going this way. It happened to have a speed of a known speed at a certain time here, but we also do it with slowing down. So the tangential component of the acceleration has to be in the negative direction, okay? And that's what we got, minus 15, wasn't it? The normal component was in the positive direction, and that was in the neighborhood of 53. So normal wins over this one because it's a great deal larger. So the acceleration is slightly in that direction. Does that make sense? Now, that done, here are your, basically your formulae, your way to represent these entities. All right, tangential and normal components of acceleration. In decomposition of your acceleration vector into a tangential component and a normal component. The tangential component is your a sub t. That's sort of strange. This is a scalar quantity, but they subscript it with a vector symbol because it's in the direction of the tangential vector. So I usually write that with a hat, remembering the a itself is a scalar quantity. That's a scalar quantity. It's just in the direction of a unit vector, tangential or normal vector. So how do we get this? Now this is a general rule. The a sub t, this component in the tangential direction, is the dot product of your acceleration vector and the tangential vector. Okay? Unit tangent vector. Okay? But the unit tangent vector is the velocity vector over the magnitude of velocity vector. So it's a dot v over the magnitude of v. That's really going to be the easiest way to do these. Anytime, just about, we are given a displacement vector, take a derivative, you got the velocity vector, take a second derivative, you got the acceleration vector, take the magnitude of the velocity vector, you can get the tangential component right by that. Okay. Now, it's also true that a sub n is the acceleration vector dotted with the unit normal vector. But that generally is not an easy calculation to make, because unit normal vector, you have to take a derivative of this, take the magnitude of that, and it's a lot of extra work. So why not, since we know that these two components add to be this, then you know what your acceleration is. I mean, you can get that. We give you your displacement vector, take the second derivative, you got the acceleration vector, you know what it is, take its magnitude, subtract from that this magnitude, the one that you already know, the one that was easy to calculate, and take, Pythagorean theorem. The square root of the hypotenuse squared minus the one side squared and give you this other side. So that's really the easy calculation one to do. Start with a displacement vector, take your velocity, take your acceleration, take the magnitude of the velocity, come up with the tangential component this way, take the magnitude of the acceleration vector minus the magnitude of this tangential that you just got and take the square root of that, and that gives you the normal, without ever calculating what the normal vector was, okay? And then having to do a dot product on top of it. So let's see if there's another way. This component of your acceleration vector, a sub t, t, that component, is a dot v, right? It's your numerator here, divided by v dot v. Well, v dot v is this thing squared, so if you can multiply it by v, basically, that's how you come up with this. So again, here's another really easy way to get that whole component, that whole, component of that vector, okay? It's your, start with the displacement vector, take a derivative, okay? Take a second derivative, dot those two, and then multiply it by the velocity vector again. And in a similar way to what we just did, you've got the acceleration vector, you already got that. You got this one now, just subtract that from that. Because the difference of your acceleration, your total acceleration vector, and your this one, that's going to give you your normal component. So it's just simply acceleration vector minus this one. Which why calculate it again? Okay, so those are the easy calculational ways to do this, so to speak. Okay, let's see if they are that easy calculation to do. Okay, there is a little proof there, and I think I just talked through just about all of that, so I'm not sure there's any advantage in trying to do it again. Let's look at example 7. What I'll do is shrink this back, and let's see. Decompose the acceleration vector, and this time they give us that off the top. Oh, no, they don't. Of r of t. Ooh, you want to go back to black, or y'all like the blue? Okay. I didn't hear your answer. I just went back anyway. Okay. It was rhetorical? Okay. All right. Decompose the acceleration vector. So we're actually looking for a of t. Okay. But we want to decompose it. Well, we'll get there in a second. Of r of t, where r of t is t squared, 2t log t. Okay. Now, obviously here, if you haven't already started imagining this, what can you tell me about t? Anything? Can't be negative. Can't be 0 either. It has to be positive. It has to be greater than 0. The log t makes it have to be that way. They didn't put it in absolute values. They just put log t. T has to be greater than 0. Okay? We want to decompose that, the acceleration vector we haven't determined yet, into a tangential and a normal component at t is equal to 0. I mean, t is equal to 1/2 or pi halves? 1/2. I thought it should be. I couldn't remember. What's your first step? Take a derivative. R prime of t, which by the way is v of t, would be, a little louder, 2t, 2, 1 over t. Everybody agree? Okay, what might you do next? Take another derivative. R double prime of t, which is, by the way, v prime of t, which, by the way, is a of t. This is your a of t. And what is it? 2, 0. Okay. Let's rewrite this one as t to the minus 1. Got it. All right. So that's your acceleration vector, period. But that's just in 3 space. That's your acceleration vector. We don't want it necessarily there. We want to know what it is in a tangential and normal components. So, what might we do? Say again? Step in here. Okay, time out. Okay, no, okay. Find t. Okay, that's what you were saying. We could, and ultimately we kind of are, but let's see, are we just looking for, what's that? Okay, everything that has t. Oh, not yet. Not yet. Oh, wait. Let's see. Can we yet? We might be able to. Now that you say that, I think we might be able to. Okay? Yeah. Okay. Basically, I would say, I was trying to read how it says, decompose the acceleration vector of this into tangential and normal components. Okay? Now, from that, I take that to mean, yeah, okay. So, let's do that. Basically, what we're looking for, A of t and A sub t and A sub n. That's what we're looking for. So, I think you're right. We can, at this point, do that. And our A sub t is going to be, now we got to do one more little thing first. And we'd have to, whether we did capital T or not, we'd have to find V of t. So let's do that. Magnitude of V of t. And what would that be? And I think we can do that of 1/2 as well. Why don't we? So let's do this of 1/2. V of 1/2. Ah, I did it again. What would that be? Yeah. What would that vector be? Okay, don't do it yet. Let's plug in what V of 1/2 is. 1, comma, 2, comma, 2. Very good. 1 over 1/2 is 2. All right, so this will be the square root of
1 + 4 + 4.
which is?
9 squared minus 3.
So that would be 3. All right, I think we're ready to roll now. Okay, our A sub t, the tangential component of our acceleration, the magnitude of that, the value of that is our A of t, which we were going to do, so let's go on and do this. Let's plug that in, A at 1/2, exactly what Nigel was suggesting. What would that be? 2, 0, -4. Is that what I heard? All right. So now we can plug in chug. That's the A of 1/2. Have we done V of 1/2? Yep, there we did it. And we've done magnitude of V. Okay, so I think we're ready to do it. So dot this one with that one. What does that give you? A little louder. A of 1/2, this one here, with V of 1/2, which is that one there. Can you do that dot product? Please say yes.
2, 0, -b.
Is what?
2, 0, -b. Right.
Okay, but a dot product is a scalar, so that'd be 2 plus 0, -6. All right. Okay. Divided by 3 then would be -2. There's your tangential component of your vector. And that's what you multiply by the unit tangent vector, which we don't know, and frankly, I'm not even sure we care at this point. Okay. Yeah, how do we get that normal acceleration, the component, normal component of your acceleration vector? Okay, so let's go back to a squared. And what is its magnitude? At 1/2. And what's that? Okay. Square root of 20, which we could say is 2 root 5. I'm not sure you want to say 2 root 5, but we said it. Okay. Minus, oh, and by the way, when you square that, like we're doing there, then that just becomes 20. So you just square the square root. That gives you 20. And what is our magnitude A of t? Didn't we just calculate that? Yes, but its magnitude would then be, okay, magnitude would be 2. Square that and you get 4. Subtract the 4 from the 20 and you get 16. We're doing that part up there, right? Okay, and square root of 16 is 4. So then you would have 4 would be the a sub n, the normal component. Yuck! Of that. So now you have your acceleration vector as minus 2 times the unit tangent vector plus 4 times the unit normal vector. All right. Let's see if that sort of seems like it makes sense. Well, you almost first have to have the drawing, and I'm not particularly inclined to draw it, so I'm going to go to the screen and let them draw it. One thing this book's PowerPoints are good for, they have most of the drawings of them. So let's see if this is indeed true. T, remember, is always greater than 0. So let's just pick a t, like 1. So when t is equal to 1, the displacement would be 1 on the x axis. And they've drawn a strange orientation here. There's x, there's y, and there's 0. Right-hand rule, it works. It's strange here. So there's 1 on x, 2 on y, I don't know where they're starting this thing. It sure looks bizarre the way they've got it here. Oh, wait, 2 on y. 1 on x, 2 on y, somewhere here, and then z would be, log of 1 would be 0. So, where in the world are you, Waldo? Is that it? No, that's a t is equal to 1/2. This is a strange thing, called the orientation of it. If this is 1/2, 1 would be somewhere up here. So yeah, that seems like it would be. At t equal 1/2, your r is 1/4 on x, and not very far on x at all. 1 on y, a bit further on y, so somewhere in here, and then actually the log of 1/2 would be a negative, and that's why you're down here. So yeah, that's kind of making sense. I still don't see their scale too well. 1 on x, 2 on y, and a negative something, negative log 2 on the z-axis. Okay, so yeah, I'll buy that. And then as t increases, x is increasing faster than y is increasing. Okay, and Z is also increasing somewhatly. So yeah, it looks reasonable. It would be going in this direction. Unit tangent vector here, unit normal vector there, which is always perpendicular to the unit tangent vector, which means pointing toward the center of curvature at that point. It doesn't have an exact center of curvature here, but at that point it does. So that's pointing that way. And the acceleration vector, it says, is a -2 on x, which, no, I'm sorry, -2 on the unit tangent vector, which would be back here. If that's a unit, that would be 2 units back here, and then 4 units here. 1, 2, 3, 4. And I can't swear that's where that true one goes, but that's what it's indicating. A slowing down in the tangential direction of the speed and a rapid increase. So frankly, to me, it seems like this curvature should be a lot sharper than that without having that big of a normal vector, normal component of the acceleration. But I can't draw any better, so I'm not going to argue with them. I'll take their word for it, or their picture for it. Okay. So I think we got what they did, if I'm not mistaken. Yeah. Okay. Good deal. All right. Ready for example 8? Let's see if we have a picture here. I guess this will be 8. Now, example 8, they're talking about non-uniform circular motion. This figure here shows the acceleration vectors of 3 particles moving counterclockwise around the circle. In each case, state whether the particle's speed, little v, italicized v, is increasing, decreasing, or momentarily constant. Okay, let's blow this up. So all we're asked to do is just basically a visual problem, not really anything we're calculating because they don't really give us any numbers to calculate with. So, this situation, we know it's moving counterclockwise because your unit tangent vector is in that direction in every case. We know it's circular motion, so the unit normal vector is toward the center in every case. Okay? So, what does this acceleration vector tell you? Okay, the speed of the particle is slowing down here because its component of the unit tangent in the component of the acceleration in the unit tangent vector direction would be negative. Of course, its normal component, you can see, is toward the center of the circle. Okay? Almost right on the money there. Okay? But yeah, that one's slowing down. How about this one?
That one's staying the same speed.
That is uniform circular motion. The velocity is not increasing or decreasing, so it's uniform speed. And at that instant, anyway, this acceleration is all centrifugal, all toward the center, in the direction of the unit normal vector. And C. The speed has to be speeding up because here's the unit tangent vector. The acceleration component in the direction of the unit tangent vector would be somewhere about like this. So that would be a positive, greater than 1, in fact. Positive meaning it's in this direction, but definitely greater than 1. And also has a unit normal direction in the direction of the unit normal vector. Okay. So yeah, that would be speeding up.
The closer the acceleration vector is to the tangent vector, the faster it's speeding up.
Yes. Well, the larger the component in that direction, yeah, the more it's speeding up. Yeah. This could be a very short component, very close to it, but it's still not speeding up very much. But yeah, it would almost all of its acceleration would be in speeding up and not in twisting. Okay, that was example 8, just sort of a visual. Particle speed decreasing, momentarily constant, and particle speed increasing. Number 9, example 9. No figure here, so we'll just write on this one. Find the curvature kappa at 1/2. Okay, I can't write very well. For the path that we did in example 7, which I still had it up, r of t is equal to t squared, wasn't it? Yeah, t squared 2t log t. Okay. We want the curvature at time t is equal to 1/2. What would help us get that? Can we recall anything we had from before? I think I remember that r prime of t, which is v of t, the magnitude of that when t was 1/2. Didn't we have that? Didn't we calculate that and find it to be 3? I think it was, no, magnitude's always positive, okay? I think that was 3. Now, is that related at all to kappa? That is also called v of t. Wasn't there some connection there between kappa and remember we flipped way back here and got kappa. Now we need one other piece of information. Oh wait, the acceleration, wait, there was a connection there. Wasn't there? Yeah, there it is. Didn't we calculate what a sub n was for that problem? Was it? That's right, it was 4. And what was our a sub n? Our a sub n is kappa, and by the way, this is at 1/2, times the speed at 1/2. And I think we know everything then, don't we? Speed was 3. That's speed squared. Okay, I knew I'd put it in parentheses for something. That was 3. So basically we have 4 is equal to kappa times 9. Right? So kappa is 4/9 for this problem. Yeah, sure enough, that's what it was. All right. Now, they did it a slightly different way, but just with the information we had, you could have gotten that. All right. This section had a whole passel, or maybe even a passel and a half. What? I'm sorry? Okay, yeah, sure. Okay, sorry about that. I skipped so many steps there, I hope you can follow.
Well, we were kind of recycling the other example.
Yeah.
That's mainly why I wasn't
The a sub n, Matt remembered as 4. Our speed was 3. And then from the previous working, we know a sub n is kappa times v squared. So that basically gets it right there. Got it? Okay. And then this, as I was saying, whole bunch of equations, okay? And nicely usable equations, hopefully. Okay? with the R of t, your displacement vector. Then first derivative of that gives you v of t. Okay? Magnitude of that gives you speed of t. Okay? And the velocity divided by its magnitude gives you the unit tangent vector at t. Now, if you have to, take its derivative. Okay? And once you take its derivative, then take the magnitude of its derivative, and that gives you the unit normal vector. By the way, unit normal vector is always going to be perpendicular to the unit tangent vector. Okay? Always. Now, you can also go back to your R of t, your v of t, take a derivative of that, and you get a of t. Now, the a of t you can split into a tangential component and a normal component. The tangential component will be, by the way, the first derivative of your speed, which is what this denominator was. The speed is what the denominator is. Take the first derivative of that, and that gives you your tangential component. That's one way you can get there. Another way is the dot product of a times t, if you wanted to mess with that. But frankly, I think easier. A was easy to get. If you know R, you know B, you know A. Okay? So do A dot B and divide by the magnitude of B, which you've already done. That gives you your tangential component of your acceleration. Okay? Now, if you want the entire vector term of that tangential component, then you can either multiply that by this, which you have to go through something to get there, or just go back and do a dot b that you already had, b dot b that is basically this thing squared. So you already have this thing, just square it, and then multiply that by your velocity vector, and you get the entire component, the entire vector form. Now, a sub n, the normal component of that acceleration vector. If you already knew the curvature, why, I don't know, but if you already knew it, and you knew this thing, the speed squared, okay, which would be basically the magnitude of v dot b, well, that would just be v dot b, that would be speed squared. Then you know that normal component. That's if you knew the curvature, okay? If you didn't know the curvature, but you had already calculated this, then just take your acceleration vector at whatever time you were dealing with, take its magnitude squared minus this thing squared, okay? And this is one place I found a little irritating. And I guess there's nothing wrong with it. But why don't they call this a sub t, like they did here? Just a sub t here, because you're taking the magnitude of it. Why make it a vector that you take the magnitude? Why didn't they just write a sub t? That's what they've been writing. Does the book do that as well? No, the book actually does do this symbol here rather than the vector symbol. Okay, good for them. Okay, so take the magnitude of the acceleration squared minus the magnitude of the tangential component squared, and that gives you the magnitude of the square root of that gives you magnitude of the normal. Or you can go back and do this. If you know that acceleration vector, you subtract that from it if you know this already. Or if you don't know that already, then calculate it, acceleration vector minus the dot product here over the dot product there. So lots of different ways to get there. Okay. But handy formulas to be able to recall. I wouldn't say memorize them. Be able to look them up and use them. All right. Any questions on that? Let's go back to Have we got time to do the preliminary questions?
We got about 10 minutes.
10 minutes, oh, for sure. All right, let's look at number 1, exercise 13.5, preliminary question 1. If a particle travels with constant speed, must its acceleration vector be 0? If a particle travels with constant speed, must its acceleration vector be 0? What's that?
It'd be a constant acceleration.
What did you say? Okay. Okay.
Well, it's not speeding up or slowing down.
Okay. But what constitutes an acceleration?
Changes.
Change of velocity,
Velocity,
not speed. So velocity can change 2 ways. One by changing speed, the other by changing direction. So it can have a constant speed, but be changing direction, must have an acceleration. So no, that should be a no. Let's see what they say. Please say no. Okay. Just say no. Okay. 13.5, no, since the particle may change its direction. Very good. Number 2, for a particle in uniform circular motion around a circle. Oh, that's nice. Uniform circular motion around the circle. Which of the vectors, v of t, that's the vector v of t, or a of t, that's the vector a of t, always points toward the center of the circle? A of t for sure. V of t points tangential to the circle always, okay? So that, oops, in the wrong section here. Better be a of t. Yes, they got it right. Good for them. Okay, let's see if I can get something to work better here. All right, number 3. 2 objects travel to the right along a parabola, y is equal to x squared. They're traveling to the right. 2 particles traveling to the right. I don't know if they're starting in the same location or what. 2 objects travel to the right along a parabola, y is equal to x squared, with non-zero speed. How could they be traveling at 0 speed? They wouldn't be traveling, never mind. Which of the following statements must be true? Their velocity vectors point in the same direction. Which one must be true? The velocity vectors have the same length. Must that be true? Or their acceleration vectors point in the same direction? 2 objects travel to the right along a parabola with non-zero speed. Which of the following statements must be true? Okay, let me go back. I said I couldn't tell from what they said. They must be from the same position. Let's say you got one there, and, oops, that's not what I wanted. Okay, you got a black one there, you got a blue one there, at the same thing. Okay. They're traveling along the parabola. Their velocity vectors must point in the same direction, their velocity vectors must have the same length, or their acceleration vectors point in the same direction. I think the velocity, if they're at the same point, which I think we have to assume, then their velocity vectors must be, they're tangential to the parabola at that point. So that better be it. Statement A, the velocity vectors point in the same direction. So they have to be at the same point. Okay, good deal. Number 4. Use the decomposition of acceleration into tangential and normal components to explain the following statement. If the speed is constant, okay, if the speed is constant, then the acceleration and velocity vectors are orthogonal. Then velocity and acceleration vectors must be perpendicular to each other. Okay? Why must that be true?
Because the speed and then the curvature go together to make the acceleration, right? To make velocity.
Okay. I think I understand what you're saying here. If the speed is constant, that means d speed dt is 0. right?
The only thing that's changing is the curvature.
Right, the direction. Okay, right. And that meant, okay. The other way of saying that, the tangential component of the acceleration vector, and this is what I think they wanted you to do, using those components. The tangential component of the acceleration vector is the change of your speed. That's the v dt, not the vector v, but the scalar v. That is it. And if the speed's constant, that's zero, so that means the acceleration has no tangential component, so it's only normal. Normal is always perpendicular. Tangential. Okay. That was 4. Let's see if they explain it anyway the same. The velocity vector always points in the direction of the motion. Since the normal vector is orthogonal to the direction of the motion, the vectors A and T are orthogonal. I don't think they did a very good job of it, but it's okay. Okay. It's true. All right, number 5. If a particle travels along a straight line, then the acceleration and velocity vectors are orthogonal or parallel. If the object is traveling along a straight line, then the acceleration and velocity vectors are, choose the correct description, either orthogonal or parallel. Say again? I saw the mouth moving, but I couldn't hear. Okay. Let me say this. If they're orthogonal, you've got circular motion. So they have to be parallel. Either, okay, 3 cases here. If the particle travels along a straight line, okay, if you're going on a straight line, its velocity is in that straight line, right? 3 things should be happening with the acceleration. It could be speeding up. If it's speeding up, it must be still on the straight line. So acceleration vector is there. It could be slowing down, still traveling on the straight line, so its acceleration vector is there, still parallel, or the acceleration may be 0 if he's not changing speed. Well, 0 is, I guess, parallel to anything. Okay, so yeah, it would have to be, I think it better be parallel, B parallel. B parallel, good for them. Okay, number 6. What is the length of the acceleration vector of a particle traveling around the circle of radius 2 centimeters with a constant velocity of 4 centimeters per second? So what is the length of the acceleration vector if it's traveling around the circle, radius 2, constant velocity, that's uniform circular motion. So what must be true of the acceleration vector, the length of the acceleration vector? Didn't we do that? You're basically your centripetal acceleration. Remember what that formula was? Why is that not doing? Okay, there we go. A sub c is equal to v squared over r. What did they tell you your velocity was? 4 centimeters per second, didn't they say? Constant, so that would be 16 centimeters squared per second squared over r, 2, that would be centimeters. This would be 8 centimeter per second squared, an excellent unit for acceleration. So it better be 8 centimeters per second squared. Let's see if we can find it. Yeah, look at that. 8 centimeters per second squared. All right. 2 cars are racing around the circular track. Let's see if we can get a circular track here. Not a very pretty circular track, but a circular track. If at a certain moment both of their speedometers read 110 miles per hour. So this one is 110 miles per hour. And you want the other one to be blue. Okay, this one is 110 miles per hour. Okay? 2 cars are racing around a circular track. If at some moment both their speedometers read 110 miles per hour, then the 2 cars have the same, choose one. A sub t or A sub n. All right. You know what I'm going to do maybe to help this a little bit? Is that going to be enough? Okay. Okay. All right. Yes. I think you can see the answer here. Okay? Now they don't have to be at the same places, but at that instant they have the same speeds. That's your little v of t. Okay? So do they have the same tangential acceleration or normal acceleration? They're both on the same circular track. Well, tangential acceleration says it's the rate at which that speed's changing. All we know is the instant they're the same, but we don't know if one's slowing down, the other's speeding up. They're both speeding up, but at different rates, slowing down. We don't know that. But we do know that the A sub n is kappa, which is curvature, and the same circular track has a constant curvature, right? V of t squared. Yes, their speed at that instant is exactly the same. This is speed squared. So sure enough, A sub n has to be the same, right? Let's see if that's what they got. They better. A sub n, good for them. Okay, let me give you some homework exercises. I know you want some. Do number 1. Do either 3 or 5 or both. Do either 7 or 9 or both. Do either 11 or 13 or both. Do either 15 or 17 or both. Do any of the odds 19 to 25. Okay? Do any of the odds 27 to 31. Do either 33 or 35 or both. Do any of the odds 37 to 43. Do any of the odds 45 through 53. Now, a couple of those are just writing. Any of those. Good deal. Excellent. Good deal. Thank you. We're going to talk about 13.6. You're not going to be responsible for that. I wish I had it finished for you today. I have it mostly typed but not run off. I'll try to have your test ready for you on Wednesday. Good deal. Right. If any of you came in late, there will be a fire drill on this campus for this building Wednesday morning at 8:30. Are any of you on this campus now? You won't? You won't come in just for the fire drill?
I'll be getting 12:15. That's just
Okay. I'll hold you to that. Okay, good deal. All right, we'll see.